Okay, so let's go ahead and get started today. Before we get started with the lecture, just a couple of announcements. The first one is, you know that once I'm done with the lecture, I normally say it's okay if you want to do the lab part at home or, somewhere else on campus. But today is an exception because today I'm getting a valve. So at some point, another instructor is going to come in the room. It's probably going to be Dr. Oliver. You guys know Dr. Oliver? You ever met Dr. Oliver? He's a really nice guy. And I'm not just saying that because he's an evaluator. He really is a really nice guy. But at some point, he's going to come into class. I don't think it's going to be until about 9:30 or 9:45. And it just wouldn't look good if none of you are here. So just for today, please don't leave until after the evaluation. And it's just for today. Okay, all other times we meet, once I'm done with the lecture, if you want to do your lab work at home, that's fine, but just for today. The other reason, there's another reason, not as important as the eval, but the other reason I don't want you to leave early today is because at 10 o'clock, the ISA for the course, Grady, he'll be here. So I just want to, introduce Grady to you so you know who he is. He'll be grading your lab work. Okay, so it's good to know Grady. Be nice to him. Okay. All right, so that was one thing. And then the other thing is, as far as the strike, if it happens next week, what I've decided to do is that I'm going to be here, but I'm only going to lecture if most of you show up. Okay. Obviously, if you're all here like today, I'll lecture. But if only like 5 people show up, then I'll just have like an open lab. Now, if it ends up being like 15 people, because there's 30 people in the class, if it ends up being like 15, then it's kind of like flip a coin, okay? But whether you're here or not, and whether I lecture or not, I mean, I always record my lectures, so. But anyway, that's what I decided to do. I was going back and forth with this, but the reason I decided to be here is because I really think it's really unfair to, all the students. You're paying a ridiculous amount of money for tuition. And, neither side, the union, I think their advice to students is to call your representative, right? And complain about, to get your tuition back. But let's face it, politicians don't listen to young people, unfortunately, because as a whole, you guys don't vote. If you guys would vote, they might listen to you, but anyway. And the union, in my opinion, that should be part of what they bargained for. They should bargain for that. If they're going to strike for a week, students should get that money back. That's a large chunk of your tuition. It's 10%. So anyway, that's why I've decided to do what I said. Okay, so if you don't show up, you're not going to be penalized. I'm not taking attendance that day. All right, so yeah. All right, if you have any more questions about that, you can talk to me one-on-one about it. Okay. Okay, so today's lecture, we're going to talk about the first part of hardware that you're going to build. Okay, here's the Otter diagram that hopefully you still have a hard copy of it, or you can look at it on the computer. It's up on Canvas. But the first piece of hardware that you're going to build is this program counter along with the MUX that goes along with the program counter. So this part of the diagrams we're going to be starting to build today. Okay, that's actually hardware number 2 assignment. Okay. Now, one thing I want to mention, and I got some emails about this, since last class, and that's for the homework, hardware number 1, that's due tomorrow. There's one thing you need to know in order for RARS to actually assemble that program and get the hex listing. And that's when you have a JAL command. And you're going to learn later on that this is what's called a jump instruction. Okay, it's a way you can go through the program non-sequentially. Well, the way RARS is set up, anytime you have a jump command, a jump instruction, this immediate can't be a number. And it has to be a label, otherwise it's just not gonna run. RARS is not gonna run. So for this command, when you type it into RARS, type the following. Just put a label. I mean, this label can basically be anything. I just have it as label 1 and then colon, and then you put JAL X0, and then instead of the 0 here, you put this same label. Okay, now, the reason why the label goes here, I'm gonna explain that at a later date. In fact, we're gonna learn a lot more about not only JAL, but the different jump commands and all the other instructions that we have in the manual. In fact, in a few weeks, we're gonna start looking how data flows in this diagram for all the different instructions. Okay, so we're gonna talk about that in more detail later on, but just so you can finish hardware number 1, you just need to type this in. Okay, you can't put a number, you gotta put a label.
Did I just tell it to jump right back to?
Yeah, exactly. See, just real quick, again, we're gonna go into this a lot more later, but yeah, this number is basically an offset. So if it's on the same line, if the label's on the same line, it's a 0. If it's, if your label goes, like in front of an instruction that's before this, then this is gonna be a minus number. That's gonna be a minus number that's divisible by 4. All right, and if your label is further down, it's gonna be a positive number. Again, divisible by 4, but again, we'll talk about why. Okay, later, so, yeah. Okay. All right, so let's go ahead and start talking about what you need to know in order to build this program counter along with its mux. And a lot of what you need to know to do this is just what you learned in CP 133. Okay, so that's why I want to review some of the things that you learned in 143, because you'll see how it ties directly into what you have to do for hardware number 2. So in CP 133, remember you learned what a mux was. What's a mux? What does a mux do?
The output is determined by what was selected.
Exactly, right? That it's basically a multi-position switch. Here's an example of a 4-to-1 mux. Right? 4 being how many inputs, and 1 being the output. A mux always has 1 output, right? But it has multiple inputs. Now, do you remember how you would determine how many bits that select input has to be? So if I have 4 inputs, how many bits would the select input have to be? Yeah, it'd have to be 2, right? Because that goes back to the, number of values that you can get from a number of bits is 2 to the number of bits. Right, so if you make the select a 2, well, it can be 0, 0, 0, 1, 1, 0, 1, 1, right? There's 4 possibilities. Here's the 2. So if I put a 0, 0 on the select, what is the output going to equal? In this example. Yeah, it's just going to equal every data that's on that input 0, right? It's just going to be easy. Right, if I put a binary 1 on the select, then the data D1 will be connected to the output. Right, you put a binary 2, D2 will be the output, and a binary 3, D3 will be the output. Right? Now, this example is showing each input being a single bit and the output being a single bit. What if I did this? What if I make all the inputs 32-bit and I make the output 32-bit? Does that change this at all? No, right? The mux is going to operate the same way no matter how many bits the inputs and the output is. Okay, so see what you learned in 133 is part of what you need to do part of this design here. It's just that the mux has more bits. Right, like you didn't deal with 32 bits in CP 133, right? Probably the most bits you dealt with, well, unless you did some really sophisticated final project, but probably the most bits you ever dealt with in for a single input was maybe 8 or so. Okay. All right, so any questions about the MUX? People remember it somewhat? Not so fuzzy maybe as it was. All right, now, also on CP 133, when you learned about a MUX, most likely, and if you're in my 133 class, you definitely modeled it as an if statement, right? Use an if statement for the MUX. But in this class, what I would like you to do is to use a case statement. Okay, and the reason for that is because when Vivado takes your code and comes up with the circuitry that's needed to, represent that code that, using to model the hardware, when it's a case statement, it tends to do a cleaner job, okay? And what I mean by cleaner in this case is that it tends to, limit propagation delays, okay? When you use an if statement, especially if you use an if statement where you have multiple else ifs, it tends to create chains of circuitry, okay, like gates in series, as opposed to something that's more parallel in nature. And see, that wasn't a big deal in CP 133 because in CP 133, the circuitry that you were designing wasn't really time critical. There wasn't, again, there might have been a final project like that, but what we typically teach in 133, there's no real time critical part to it. But in this class, as we're going to get into more detail later, there is time critical, there is a time critical nature to this design here, this Otter microcomputer, okay? So you always want to do designs where you don't have as many propagation delays. And all I mean by propagation delays is stuff to go through. The more stuff you have to go through, like gates in series, well, the longer it takes, okay? And there's a portion of this circuit where if it takes longer than a clock cycle, well, it can cause the whole thing not to work. Okay, and again, I'm going to get in more detail exactly where that is later on, but that's just kind of like an overview. Okay, so the short of it is that when you do a MUX in this class, please use a case statement. And let me give you an example here, using this 4-to-1 MUX here. So, as you probably remember from CP 133, you always start off with a module name. Now, just as a reminder, remember, Vivado doesn't like spaces and names, right? So you don't want to put spaces anywhere in the file path. Like you don't want to have spaces in any of your design source names or, sim names or folders or anything like that. And same thing with names of your modules and inputs and outputs and things. You don't want spaces, right? Most people use an underscore for module names and input and output. Just a reminder about that. So your module name, then of course, remember you have to declare your inputs and outputs. Okay, so I'm not going to write the code specifically. I'm just kind of doing an outline for you. Okay? And then also with inputs and output names, I'm pretty sure if I remember correctly, that Vivado doesn't like names that start with numbers. Like you wouldn't want to put one input or just put one. Now putting input 1 or something like that, or PC1, PC2, it's okay. But if you start with a number and a name, sometimes that causes a problem. Okay, so here's a another CP 133 sort of pop quiz question, and that's in 133 you learned about 2 types of logic circuits. Remember what the 2 types were? One type starts with a C, and the other type starts with an S. Yeah, I think I heard it. What was it? Yeah, combinational is one, and then did you have the other? Yeah, sequential, exactly. And what's the big difference between the 2? What's the big difference between combinatorial, combinational, and sequential? Right, it has a clock input. Sequential circuits always have a clock input. And then what's the other big thing about sequential that's different than combination? What is it? What does sequential have that combinational doesn't have? Memory, exactly. And that's why you need the clock, right? Because you have a memory register, you need a clock input. Okay? So knowing all that, right? What do we have here with the mux? Which type is it? Combinational, right? Because it doesn't have a clock input, muxes don't have memory. So in System Verilog, you're gonna use an always home block. Always underscore home, right? Home short for combination. And then you gotta have a begin. Sorry. That's a begin. Okay, and then like I said, we want you to use a case. So remember that when you have a case statement inside this parentheses, we call it a sensitivity list. Because whatever you put there, when that changes, that's when the case gets evaluated. So what are we gonna put here? What input do we want to put there? Yeah, the select, right? Because when the select changes, that's when we want to reevaluate what the output's gonna be, right? 'Cause the output depends on what the select is. So you have case, select, and then you just list your options. 0, 1, 3. Now, I'm pretty sure that if you just put the numbers like this, it will default to base 10. Okay, I'm pretty sure, but if you get an error, you might have to specifically tell it it's decimal with the D. Okay, but I'm pretty sure if you just do that, it will default to it. But then you just set your output to whatever the input should be for that select value. So, you know, in this case, if we're using these variables here, when the select is 0, we want to set the output F to input 0. Is 0. Now, another thing that we don't, or most instructors, including myself in 133, perhaps don't stress enough, that is important in this class, is that in CP 133, you know, we're not that picky with how you name things. Like you can just use like A, B, you know, very generic type of names. But in this class, you want to be descriptive, okay? Because well, my screen went dark here. Hold on one second. See, look how many muxes we have in this audit. You know, here's the mux that's part of the program counter. Okay, so that's the one you're gonna be building today. There's another mux over here. There's another mux here. There's another mux here. This ALU that stands for Arithmetic Logic Unit, you're gonna see that this is basically a big mux. Okay, so you've got like a handful of muxes. So if you've got the same names for your inputs and outputs for all your muxes, when you go to troubleshoot this, it's gonna be a nightmare, right? Because you're gonna have like 5 different inputs to different muxes that have the same name, and you're gonna be like, what input is this? What mux? Okay, so a good approach is, like in this case, because this mux is connected to the program counter, you know, maybe you would want to call those inputs like PC underscore mux underscore 1 or something like that. You know, come up with something that works for you that's descriptive, that tells you, oh, that's the mux for the PC and it's that input. Okay. All right, but then you would just fill this out. And then what you always have to have is your last option in a case statement. Yeah, you need a default. Can anyone tell me what happens if in a case statement you don't put a default? Can you tell me what happens in an if statement if you don't put an else? Like if you just have, you know, if, and then maybe like an else if, but then you don't have an else. A latch, right? If statement, if you leave out the else, it creates a latch. Well, case statement, you leave out a default, it will create a latch. Okay, it's you'll get a warning, it will say inferred latch. And what that means is that even though this is supposed to be combinational, it's adding memory to it, it's adding additional circuitry. Okay, now again, in CP 133, because the designs weren't time critical, you could get away. In fact, you know, I saw when I graded the individual projects last quarter for like the 4-bit multiplier and in some of the final projects, not many final projects, but there was, well, there wasn't a lot, but there was more than what I would hope in the individual final project where people had inferred latches. Right now, the design still worked, okay, but it was creating additional circuitry, you know, like putting memory where you didn't need it. And while you could get away with it in CP 133, you can't get away with it here. If you have any inferred latches, it's likely gonna cause a timing issue. At the very least, it's gonna cause a timing issue. And then it's likely to make the whole thing not work. Okay, so you have to be really aware not to have any inferred latches. Mhm.
Variable that.
Yeah, that's a really good question. Yeah, I would say that's a good thing to have in common within the team. Yeah, like you're, again, all doing your same thing, so it's not gonna be the same design, therefore you don't run into the same problems. But yeah, to have the same names would be a good idea for your team. So yeah, that's a great suggestion, yeah. Yeah, I would recommend that. Yeah. Okay, so just finishing this, you know, you gotta end your case with an end case. There we go. End, oops. End case. And then you gotta end the begin. And then you have your end module. Okay, so again, the purpose of this is just to kind of give you an outline, right? And then, you know, for your specific, this specific mux here, you know, you're gonna have to, you know, make it more exact, of course. Okay, but any questions about the case statement or anything up to this point? I'll take Audrey's question out and yours. You can make the default, whatever you would like to. You could just set it, oh, you know what some people do is, because remember, well, you know, provided you have 32 bits, like I've seen some people make the default like dead. You know, heck, because DE, you know, DEAD is all characters and hex, right? So people come up with some pretty creative, you know, hex. I've seen dead. Of one. So yeah, but you can make it anything you want. And then Michael have a question?
Yeah, do you have to end the always count also or no?
Did I make a mistake here? Well, yeah, it's this here, right? Because the always comb the begin and then this end ends it. Yeah. Yeah, that's one thing that always gets me, especially when, well, you'll see later on in the quarter, there's a couple of modules where you're gonna have like nested, like, you know, like a case nested within a case or an if, you know, nested within a case. And when you start getting into like nested things, that's when it's very easy to have like a missing end somewhere or you have an extra one. That's the thing that always gets me. I make that mistake all the time. So yeah, it's good to always double check that. Okay, so any questions up to this point? Oops.
For the end or the default, is that, so when we want to create memory, we leave it out, like I remember that, and so is that in an always comb, are we always gonna have a default or a else?
Yeah, because, yeah, no, you're exactly right, that if you leave it out, you're gonna create memory, which is a sequential circuit, right? But a mux, you know, anything where you're using an always comb, you want it to be combinational, otherwise you would be using the other one, right? Which is always FF, so yeah. Yeah, it's an always comb block combinational, you need a default.
But in some cases, under like an always FF, where we want memory, we
Right,
don't want it.
yes, yeah, that's true. Any other questions? Okay, so the next thing is to review from 133 a register, because The other part of what you're building today, right, you got the MUX, but the other part is this program counter. And you probably talked about counters in 133. But maybe, something that might have been not so apparent in 133 is that a counter is just a register that increments by a certain amount. Okay, so a big part of a counter is a register. Okay, so in 133, okay, so you see here, counter is a register plus, an increment. And we'll increment so much every clock cycle. So here's a counter. Now, do you remember what LD stands for? Right, that's a load, which is, the same as enable. In this class, it's also the same as a write. Okay, so load, enable, write mean all the same thing. And then RST, that's what? Reset. And then we have our input, D input here. Now I made them 4 bits. Because you had a register in one of the, well, again, if you took my class, because some of the labs are different depending on the instructor, but I would imagine at some point everyone had to do a multi-bit register. And, people that took me for 133, there was that adder subtractor with memory that we had a 4-bit register. This here, of course, is 32 bits. But the idea is the same, right? It's just more bits. So you got your output, which is Q. So do you remember how a register works? Now, first of all, again, it has a clock input, so it's sequential. But do you remember how a register works? Like, for example, if we activate reset, what's going to happen? Yeah, Q just goes to 0, right? Depending on how you do your priority, like if the reset's the first one in the if statement, then that has priority over all other inputs and the reset's going to happen, which is typically what you want. Okay, typically your reset is your highest priority, and you'll see in this case that's true. Okay, how about what's going to happen when the load is activated? Like, what does load mean? Right, exactly that. When load is activated, Q is just going to become equal to whatever's on the D input. And if I'm not loading and I'm not resetting, what am I doing? What is the register going to do with neither loading or resetting? Yeah, it just holds the previous value, right? That's the storage state. Okay. Now, also, again, this gets back into the difference between asynchronous and synchronous. Everything we just said is true when you have a synchronous case, as long as you have the active value during the appropriate edge of the clock. And I mentioned this earlier, but I'll mention it again because it's important. For the Otter, that's the name of our microcomputer, the Otter. All inputs are active high. So all inputs are active high, and all inputs are synchronous except one. Okay, the one input that's asynchronous has to do with the reg file. Okay, so, and we're going to talk about the reg file in a couple of classes, but for what you're doing today for this program counter, everything is synchronous and everything is active high. The other thing is we want to make all our modules rising edge trigger. Okay. Okay, so let's see how we would do a register using an if statement. Okay. So again, you always start off with a module name. Like maybe you would want to name this like PC. You could just call it PC. And then you could call this like just PC_mux or something like that. But you want a module name, of course, and then, you know, declare your inputs and outputs. Okay, now because this is sequential, what am I gonna do next? Instead of always comb, because it's sequential, you do a what? Yeah, it's an always up out. And you need the at symbol, and then do you remember what goes in the parentheses here? Since we want it to be rising edge. Yeah, it's positive block. Yeah. Because remember, what you put in the parentheses of this always FF, that's when this block is gonna be evaluated. Right, so since we want it synchronous on the rising edge, every time there's a 0 to 1 transition, right, a positive edge, that's when we want this if statement to be evaluated. Okay? So then comes the begin. And then you start your if statement. So again, you want to make reset the highest priority. So we start with the reset, if that's active, then we just want to make Q equal to what? 0. Now, this gets into another thing that comes up in CP 133. Remember, you have the equal, and then you also have that. You remember when to use that one and when to use that one?
Everything up to the top.
Okay. Yeah, exactly. The equal is when you're assigning outputs in a home block, like I did over here in the case statement, right? This here is when you have sequential, right? So this would be for an FF block. Right, so like here, when you assign Q, you don't put equal, you have to do the arrow. And then you would just assign it to 0. One way you could do it, let's see, if we made this, well, it's just 4 bits, so you just do 4 zeros. Now, when you're doing yours at 32 bits, you might not want to write 32 zeros, so you could do hex. And the thing that's tricky with that gets some people is that even though the hex for 32 bits is 8, right? Takes 8 characters for 32 bits. When you use hex, you would still put the number bits, like you would put 32 tick mark, then H, and then you would put the 8 characters. Right? Big mistake, and I make this mistake all the time, is I put 8 because I think, oh, 8 hex characters. But you have to put the number of bits, even though you're doing hex. Okay. All right, and then we would have an else if. Load. Right, that if we're not resetting and we're loading, we're just gonna set Q equal to whatever's on the D input. By the way, these are semicolons, look more like gated. Now, am I gonna put an else? No, why not? Yeah, because you want memory here, right? Because if we're not resetting, we're not loading, we want to store. So remember also in Verilog, the double backslash, that's a comment, right? So you see no else, means storage. And then we just got to end the begin. And module. Okay, so so this is a register, right? This is going to provide the register part. Now, to get a counter, you have to increment the output in some way. And the way we're going to do that is shown in this diagram here. And let me move the camera. Okay, so here's the MUX. Here's the program counter, and this block is basically the register. This additional block here with the +4, that's what makes this a counter. Okay, because again, a counter is a register plus some increment. Okay, and here we're incrementing by 4. Okay, a +4. The reason why that's +4 is because of what we talked about earlier last week. The memory module. My screen keeps going dark on me. Get this back out. Okay, the memory module is right here. Notice that the output of the program counter, okay, so this output right here, is connected to an address input of the memory. Now, there's 2 address inputs. Address 1 is what connects to the output of the program counter. Address 2 connects to something else, and that's going to come up in a future class. But right now, the output of this program counter, it goes to an address input of the memory module. And you see the purpose of the program counter is that it provides the address of the instruction being executed. Okay, so here, right at the output here, is the address of the instruction to be executed. Okay, so, question.
What's the purpose of the little box with the dash sign going from the program?
Oh, right here.
Yeah,
That, I believe that's just to indicate that if you look real close here, and it's hard to see because of the resolution. If you look real close here, there's 32 bits coming out of the PC, but we're only using bits 2 through 15 for this address. And there's a reason for that I'll talk about at a later point. Okay, but yeah, I think it just means that there's like a reduction. Now, it doesn't always, oh yeah, it does it over here too. It does the same thing. There's like 32 coming in and it's less, but then sometimes it doesn't show the minus, like here it doesn't show it. But that's all it means. It's kind of like you're not using all the bits. Yeah. Okay. All right, but you see now that you know that the address of the instructions to be executed is what the PC is providing, it should make sense to you that it connects to the memory module. Right, because remember in an earlier class, we said that the memory module has these different segments. Remember what the segments are? Like 3 segments.
Code,
Code,
MMI,
what's that?
MMIO. No.
Right, and well, MIO is part of the memory module, although it's not part of what we call real memory, but yeah, that's a segment. There's code, there's MMIO, there's data, and then there's also one called stack that we're not going to get to for a long time. But here, the one that's important is the code segment, because what's in the code segment? The instructions, that's where the program is. And do you remember specifically what device that program is in? In fact, you learned how to program it in hardware number 1. Remember that there's something within the memory module? The program, exactly. That the code where the instructions are, right, your program, that's held in the program. Which is part of the memory module. Okay, and then how many bits is an instruction? Like, how many bits did you have to write out for all those hex? 32, right? And each register that's in the memory module is 32 bits. And in this class, we call 32 bits a what? A word. And because you can't cross word boundaries like we talked about last time, your addresses for your instructions are separated by 4. Okay, your first instruction is always going to be at address 0. See, notice that one of the inputs to this program counter is this PC reset. And PC reset. Now, in that diagram that came out of the lab manual, it's labeled PC reset. Here it's just reset, but it's the same thing. Okay, where it says reset here is that same PC reset. Well, if you look at where it's coming from this FSM up here. See, this FSM is providing the reset to that program counter. And we'll talk about later on how the first thing you do, one of the first things you do, like one of the first states in that FSM is to reset the program counter, right? Because you want to start at the instruction that's at address 0. You always start at address 0 for your first instructions. But then after that first instruction gets executed, you want to go to the instruction at address 4, right? Because that's where the next 32-bit instruction is. And then after that instruction is executed, you want to go to the next instruction, which is at address 8. So you see, that's why we're incrementing the program counter by 4 after an instruction is executed, because each of the instructions is separated by 4 in address. Okay? See, this shows how hardware and software are directly related, right? Because in the software, right, when you're looking at the instructions and it's 32 bits, that's determining what the hardware has to do. Okay?
So when you're writing that, do you literally just put PC, whatever, PC plus 0, 1?
Right. Yeah, that's exactly where I'm headed, right? Because when you build this, you're gonna have an always comb block for this, right? And that's gonna be a separate file. Like you'll have muck, you know, maybe you'll call it pcmux.sv, and it will just be an always comb. Then you're gonna have another file, right? That's gonna be an always ff for this register. And then you're gonna have a top module, right? Because now you gotta connect the mux and the register together. And in the top module, you're just gonna call this is gonna be a internal signal. Now, you're gonna be more descriptive, but just for the sake of being quick here, you know, say it was T1, right? And you call this T2. Well, now in that top module where you're making all the connections, just use an assign statement. Just assign whatever you call this to this plus 4. Yeah, so this is very easy to model in System Verilog. It's just going to be one assign statement. And you just put it in the top module where you're making the connections.
Looks like when we were making like OR gates in 133.
Um,
The sign.
Say that again, what part?
133, I think, in one of them.
Oh, like one of the
OR
activities.
gates, Yeah.
Yeah, yeah, exactly. Yeah. And there was cases like in one of the labs too, where you have to do an assign, like in a top module. I can't quite remember what it was, but yeah, it's the same idea. So, yeah, so this is gonna be, like I said, it's a structural design. You're gonna need 3 modules, right? One for the mux, one for the register here, and then a top module that connects everything together, and then also takes care of this with an assign statement. Now, again, don't use T1 and T2, you know, use something more descriptive. Yeah, you know, just so, again, when you have to troubleshoot it, you know, you don't have to, you know, it's just, you know, good bookkeeping to use more descriptive names. Now, the next thing I wanted to talk about was, remember also in Vivado, when you're modeling, you know, any sort of circuitry, you need to know what the main inputs and the main outputs are, right? Because the main inputs and main outputs, that's what's going to be in your top module. Okay, so that's where your high-level black box diagrams is useful, right? Because whatever main inputs and outputs you have, you show it in your high-level black box diagram. So what are my main inputs gonna be here for my high-level top module? So you gotta think, there's like a dash box, kind of like this. Kind of goes like this. Kind of like that, good. Right, see, these are your main inputs. See, these inputs here of the MUX, the JALR, JAL branch, if you look at the diagram here, see, these go over to this module called a branch address generator. Okay, and we're gonna learn about what that is in a future class. Okay, MTVEC and MEPC, those come from this module here, which has to do with something called interrupts. Yeah, and that's something that I'm not sure yet whether we'll have time to talk about because we've already lost one day due to the holiday we just had, but we may get to that, but there's a chance we might not either. And then let's see, and then we already talked about reset. Reset connects to the output of this FSM up here, and then PC write is also an output from the FSM. PC source, it's coming from this CU, which stands for control unit. And then can you guess what DCDR stands for? Decoder. See, CU is control unit, and you all remember FSM, I'm sure. Finance state machine. So you see your control unit has two parts to it, an FSM and a decoder. And we're going to talk about this in a lot more detail, but just real quick here. The outputs of your decoder, they go to all the selects of the muxes. Right? So you see your decoder is controlling what your muxes is selecting. And then all your writes and your reads and like your reset, that's coming from the FSM. Like your FSM is determining when we're getting information, when we're storing information, when we're resetting the whole thing. Okay. Yeah, so getting back to this. So yeah, you're gonna have a bunch of inputs here, right? You're gonna have, write, PC write, you're gonna have PC reset. You're gonna have PC source. Then all these here. So you got a bunch of inputs. What you got? 1, 2, 3, 4, 5, 6, 7, 8. You got like 7 or 8 inputs. 2, 4. Well, and then also the clock, right? You need a clock for the register. So you'll have a clock. So there's like 9 inputs. How many outputs do you have? Just the one. Right? You just have this one that's applying the address of the instruction to be executed. So, see, the way this works is that the first thing that's going to always happen, and again, the FSM is going to determine this. The first thing that always happens is that you reset your program counter because you want the address of the first instruction, which is always at address 0. And then after an instruction has been executed, it will get incremented by 4. The address will get incremented by 4, and it's going to be sitting right here. And as long as we're going through the program sequentially, PC source coming from the decoder is going to be set to 0. So it chooses that next instruction that's 4 an address away from the one that's just been executed. Okay, and then to update the address, this PC write has to be active. That's what actually gets the new address to the memory module, right? Because remember again how a register works. See, the write is the same as a load or an enable. Okay, so that next address is going to be sitting here until this is activated, and then also the clock edge has to happen because it's synchronous, and then that updates to the next address. And if you're not jumping, or if you're not branching, or if there's no interrupt, you're always just going to go sequentially through your program. But just like in other programming languages, in assembly, there's ways to jump in your program. There's ways to go through your program non-sequentially. Okay, there's what's called branches, which are basically conditional jumps, and a jump, which is an unconditional, where you can go through your program non-sequentially. So if you want to jump or branch, well, then your PT source is going to be a different value. Okay. So anyway, so I just wanted to point that out. Again, we're going to talk about a lot of this in a lot more detail as far as the jumping and branching. In fact, next class is going to be on branch instructions and assembly. Okay, but for today, and I think, let's see, I just want to make sure, is there anything else I wanted to talk about before I let you start working on your assignments, I think? Well, the only other thing I wanted to add here, and, okay, the only other thing I want to add is that, we talked about the program counters providing the address of the instruction to be executed. That's what's going to be right here. The actual instruction, right, the actual 32 bits of the instruction, like what you see in your manual, that's going to be at this output here, D-out1 of the memory board. So address of the instruction to be executed, instruction. And look where that instruction goes. It goes to this reg file, and it also goes to this what's called the media generator. So the reg file and media generator, it's going to take bits of your instruction and do something with it that we're going to talk about in a couple of classes. Okay, so we're just starting into like how this all kind of ties together. We're just starting into it, so if I don't expect everything at this point to be like crystal clear. I'm just kind of giving you some preliminary information, and then we're going to go into more detail, and it will become clearer, more clearer, hopefully, as we go. Right, but what hardware number 2 is to build this and test it out. Now, remember, hardware number 1 was kind of an oddity. Okay, it kind of had its own stuff that you turned in that we talked about last time. Hardware number 2 is the first, like, normal quote unquote hardware assignment. So remember that on Canvas, I have what you turn in, the criteria for the hardware assignment. So if you go on Canvas and just click on the hardware assignment file, you'll see that there's these 3 items that you turn in for your hardware assignments. The first one is the structural design, which is the elaborated design schematic. And you can read what it says there. Again, we talked about how you don't want like long chains of gates, and as long as you use a case statement for the MUX, it should be okay. Like I said, the only time usually you'll run into where you'll have long chains of gates is that you use an if statement that has lots of else ifs. Yeah, you want to make sure again that there's no unintended latches. It says no latches, but it should be no unintended latches, right? Because again, if you want memory, it will have a latch, but if it's combinational, it shouldn't have a latch. And again, it just emphasizes that unintended latches can cause your whole circuit not to work. You want to provide simulation diagrams. I'm not going to require that you turn in simulation diagrams for like the MUX and the PC separately. I only require that you turn in a simulation for the whole thing to show the whole thing is working. Because, if the whole thing is working, that means both of these have to be working on their own. Now, the proper order of things is that, even though you don't have to turn in a simulation for the MUX and a simulation for the register, you should do it before you do a simulation for the whole thing, right? Because if the whole thing doesn't work, you're going to have to do it anyway. So you might as well do it in steps and make sure that the individual ones are working before you sim the whole thing, right? It's just common sense. Let's see, what else here? Yeah, this is important for the grader, that if you have a large simulation, like you've got, quite a few test cases, like break up the screenshots, like don't try to fit it in all one screenshot and the person can't read anything. Okay, the grader has to be able to see what the data values are. You know, sometimes I think students feel like, well, if the waveforms are green, that means it works. Well, not necessarily. They can be green and have the wrong data. Okay, so that's why the grader has to see the data. So if you have to do multiple shots, you know, do that. And then, now this is different than what I require in 133. I don't require any code until the very end, but in this class, because it's so important that each module works the way it should, otherwise the whole thing's not gonna work, for sure. We do wanna see your code for, the individual blocks. So you wanna provide your code, and then please do the highlighting and make it readable, for the grader. Okay? All right, so do you have any questions about anything? Question?
In the first part, you say if the design shows the latches, please show an example of the design that shows a latch.
Well, it will show circuitry that, let's see. If I can remember, a latch looks like this, like if you have either a NAND gate or an OR gate, you know, pairs, where it looks like this. Yeah, I don't know if you remember from 133, this is called a cross couple, like cross couple NANDs. So it could either be cross couple NANDs like this, or it could be cross couple NORs. Now, there can be other stuff too, like, you know, there can be other gates, but when you see this, that means it's a latch. Okay? And like I said, if you have a latch where it's not supposed to be, like if you have a latch being generated by an always home because, you know, you're missing a default, let's say, you'll get a warning. You know, that's one good thing about Vivado. I don't think I've ever had a case of Vivado where there was an unintended latch that it didn't tell you about it. Like, you will definitely get a warning. It will say inferred latch. It won't say unintended. It will say inferred latch. Yeah. So let's see, any other questions? All right, so like I mentioned at the beginning of class, just for people that came in a little late, today at some point, an evaluator is gonna come in the room, so please, you know, normally I say after a lecture, if you wanna do the lab part at home, you can leave, but please today, stay. I think the evaluator is gonna be here, like I said, around 9:30 or 9:45. And then once the evaluator is done, you know, you could leave after that. Also, Grady, the ISA should be here at 10, and I want, you know, to introduce Grady to you too. So, at this point, if you haven't finished hardware number 1 that's due tomorrow, that's probably what you should work on, right? Because that's the next thing due. And then after that, you can start working, building on this program Counter Mux. That's gonna be due Wednesday of next week. Okay? Everybody good? Any questions before I shut off the video? All right.